In this video, we're going to be talking about light and the electromagnetic spectrum. So at this point, we're getting into more of the structure of the atom as a whole, and much of our understanding of atomic and molecular structure comes from looking at how light interacts with matter. So having an understanding of light is important for understanding where our current models of the atom sort of come from and how they've evolved over the years. So we're going to get a little basis in this before we dive into some next stuff. So when people refer to light, they most commonly mean visible light, the light that we can see, but not all light is visible to us. As a scientist, the word light is really interchangeable with the phrase electromagnetic radiation, which is more all-encompassing. So visible light is one type of electromagnetic radiation, but there are all sorts of other types that we can't see as well, but they all have a lot in common. So light is more than just what we can see. And what all electromagnetic radiation, all types of light, have in common is that they travel through space as waves. And waves have several different sort of measurements or features that we should try to be aware of. Let's see if I can draw this as accurately as possible. That's pretty good. So you can think of a wave as having sort of this oscillating pattern. My drawing is a little bit pointier than optimal. Round out those peaks and valleys a little bit more, but good enough. So there are a few different features of waves that we should be aware of. So the distance between sort of two similar points on the waves. So it's usually easiest to think about it in terms of like peak to peak, or in this case I've drawn it kind of valley to valley at the bottom. This is known as the wavelength. It is very literally the length of the wave. It is symbolized by the Greek letter lambda, which I always think kind of looks like a little playground slide, personally. So this is length of wave. It is a distance, so it has units of distance, things like meters or millimeters or nanometers, depending upon what type of electromagnetic radiation you are talking about. So we can think of this as the distance from peak to peak. And our units are going to be things like meters, centimeters, nanometers, etc. We also have what's known as the amplitude. So if we imagine that there is kind of a midline running down our wave here, it's not actually part of the wave, but just imagining that like this oscillation is happening around some middle point. The height of our wave from that midpoint to the peak is known as the amplitude. So that's the height of the wave from midline to peak. So we're not going to talk much about amplitude in this course, because it's not something that really comes into play for us. Wavelength is an important factor for much of chemistry. amplitude is actually more important for sound waves than it is for light waves. So you'll hear a lot more talk about amplitude if you're talking about waves in the context of sound, because sound waves are a little bit different on the physics side of things, but still similar type of feature, so kind of good to be aware of. So wavelength is more what we will focus on, and wavelength is related to another factor that can't be drawn on the graph here. It's not a physical feature, known as frequency. So frequency is symbolized by the Greek letter nu, which is sort of a squiggly V. My nu is not very good looking. That one's better. So it's mostly kind of a curly V with like a little flag on the left-hand side. And what frequency is measuring is how many complete waves pass by a given point per second. So if you imagine standing somewhere, standing still, and a wave is passing by you, the frequency is measuring how many times, how many complete oscillations make it past you every second. So the frequency has units known as hertz, which is the same thing as inverse seconds. So it is very literally per second how many waves are passing by a particular point. So we'll be talking a lot about light in terms of what are known as photons. So light travels through space as waves. Photons can be thought of as light particles. So light does have some particle-like properties as well. And a photon you can think of as being sort of the smallest packet of light energy that you can have. Or like a light particle. So these have properties of both waves and particles, depending upon the context. And we'll talk more about that kind of as we go through things. And so photons are sort of the smallest packet of light and the smallest packet of light energy that you can have. And these ideas of wavelength, frequency, and energy are all interrelated mathematically. So we have one mathematical relationship that relates wavelength to frequency. So the only new variable here is c, which is the speed of light. Which has a value of 2.998 times 10 to the 8th meters per second. So then lambda is our wavelength, which if we're using the speed of light in meters per second, we want our wavelength in meters. Those length units need to match. So if you have a wavelength that's in a different unit, you either need to convert that to meters or convert the speed of light into whatever unit your wavelength is in, so that those length units match. And then the frequency was nu, which is hertz or inverse seconds, which are the same thing. And again, if you're dealing with a frequency that for some reason is in another unit, which is not common, because your speed of light is in meters per second, those units need to match as well. Then we also have a relationship between energy and frequency. So E is the energy per photon of light, and it is in units of joules. Which is symbolized by the capital letter J. So the joule is the SI unit of energy. You'll see it a lot going forward in chemistry. H is a constant known as Planck's constant. Which has a value of 6.626 times 10 to the negative 34. And that has a unit of joule seconds. Nu is once again our frequency in this as well. You'll also sometimes see these two equations, if you kind of squash them together, you can relate energy directly to wavelength as well. If you solve this for frequency and sub it in over here, this is what you get. So you can use those relationships together to relate all three of these different variables however you need. So let's take a look at a quick example. So let's calculate what is the frequency of light with a wavelength of 550 nanometers. And I will tell you that 1 meter is equal to 10 to the 9th nanometers. So why don't you pause here and try to solve this one on your own first, and then I will go through it. So in this one, we are looking to relate wavelength to frequency. So that means we are just going to need this equation, since that relates those two variables for us. So the one thing we want to be careful of here is our units. So you will be given the speed of light in meters per second. And again, we need to make sure that those distance units match. So if this is in meters, this needs to be in meters, which it is currently not. So the first thing we want to do is convert. You can either convert the speed of light to nanometers per second, or you can convert the 550 nanometer wavelength that you're given into meters, which is what I'm going to do. But it should get you the same final answer either way. So we're told that our wavelength is 550 nanometers. To convert that to meters, we can use the conversion factor that 1 meter is equal to 10 to the 9th nanometers. The nanometers goes on the bottom so that those units cancel. Meters goes on the top since that's where we want to end up. And that gets us 5.50 times 10 to the negative 7th meters. So now that we have that, if we are looking to solve for frequency, that will be the speed of light over the wavelength. So our speed of light was 2.998 times 10 to the 8th meters per second. The wavelength in meters that we just found is 5.50 times 10 to the minus 7th, which gets us a final frequency of 5.45 times 10 to the 14th inverse seconds. You'll notice that for our units, we've got meters on the top cancels meters on the bottom, and we're left with this 1 over seconds, that we have seconds in the denominator of this unit. So that's the same thing as seconds to the minus 1, or inverse seconds, which is where we want to end up for frequency. So let's do one more. What is energy of a photon of light with a frequency of 315 megahertz? And I will tell you that there are 10 to the 6th hertz in 1 megahertz. So pause here, give this one a try on your own, and then we will do it together. So in this one, we're looking to relate frequency to energy. So that is the second equation that we talked about. So we're going to need, oops, hey, come here. There we go. We're going to need this little friend. H is a constant that you will always be given the value of. V is our frequency. We do need our frequency to end up in hertz here, since our Planck's constant, or H, is in joule seconds. We need the frequency to be in inverse seconds so that those cancel out, and we get units of joules. So we're going to need to convert our frequency. We were given 315 megahertz in 1 megahertz. There are 10 to the 6th hertz. So that gets us a frequency of 3.15 times 10 to the 8th. And now that can get plugged in along with our value of H, which was 6.626 times 10 to the minus 34 joule seconds. The frequency we just found in hertz, which is the same thing as inverse seconds, was 3.15 times 10 to the 8th. So that gets an energy of 2.09 times 10 to the minus 25th joules. So we can do these types of calculations interrelating any of these 3 different parameters: wavelength, frequency, energy. We just need to make sure we're paying attention to the units and making sure that things cancel out appropriately. So the last thing I want to talk about briefly is the different regions of the electromagnetic spectrum. So the electromagnetic spectrum essentially just categorizes different types of light according to their wavelength or frequency. You can think about it either way. And the distinctions are made largely on how different types of light interact with matter. So different regions of the electromagnetic spectrum interact with matter in different ways and give us different types of information. So that's kind of where these different distinctions are coming from and where the cutoffs are coming from. So we're not going to talk too much about the specific types and what they all do, because really it's all the same stuff. It's all electromagnetic radiation. So we're starting here at the highest energy, the highest frequency, and the shortest wavelength. and working our way down. So the highest energy type of electromagnetic radiation we've already talked about is gamma rays. We talked about these in our nuclear chemistry unit as gamma radiation is one of the main types of radiation that's given off by nuclear processes. It is pretty darn dangerous because it is so high energy that it is able to do cellular damage. It's able to cause chemical reactions in your cells and in your DNA, which is not so great. And things in the gamma ray region have wavelengths on the order of 10 to the minus 12 meters or so. You don't need to like memorize these numbers or anything. I'm just trying to give you a sense of like what the range is here that we're talking about because it is very broad. Next up on the list is X-rays, which is exactly what you think they are. X-rays are the radiation that is used in medical X-rays to see what's going on with the bones inside your body. So these have wavelengths on the order of about 10 to the minus 9th meters or so. They are lower in energy than gamma rays, but still high enough that in substantial doses, they can do some cellular damage, which is why you want to try to limit your exposure to X-rays and not just go get an X-ray every day for funsies. So working our way down. Next is ultraviolet, also commonly referred to as UV. Which has wavelengths on the order of 10 to the minus 8th meters or so. Ultraviolet radiation is still high enough that it can do some cellular damage, much more limited than the higher energy ones. But it is the UV rays from the sun that can cause skin cancer if you don't protect your skin and you spend a lot of time outside. So there is still the potential for cellular damage there. Ultraviolet is so named because it is just above violet in energy. So the next segment that we're getting to is visible light, with violet being the highest energy and red being the lowest energy. So we would have red, orange, yellow, green, blue, violet in that order. And the visible spectrum is about 4 times 10 to the minus 7th meters to 7 times 10 to the minus 7th meters. Just below visible, just below red in the energy spectrum here is the infrared, also known as IR region of the spectrum, which have wavelengths on the order of 10 to the minus 5th meters or so. Then we get into microwaves, which are on the order of 10 to the minus 3rd meters for their wavelength. So microwaves are what is used in microwave ovens to cook food. There has been a lot of, I'm lacking in words right now, concern, I guess, in the past that microwaves could, be dangerous and, are hurting or damaging your food and could be damaging to you. But they're so low energy that that is not possible. They are lower energy than visible light. Visible light is not damaging to us. They're even lower than infrared, which is lower than visible. So microwaves are a pretty low energy form of radiation. They cannot do any damage to you or your food. The way that microwaves are able to heat up food is that the interaction between the microwave region of the spectrum and matter is basically that it makes molecules spin faster. And it's particularly well suited to making water molecules spin faster. And fun fact, basically all food is mostly water. So whatever you put in the microwave oven, the water molecules in that food start to rotate, and it's pretty literally the friction between molecules that generates heat that heats up your food. And then last but not least in our spectrum here is radio waves, which are on the order of 10 to 100 meters in wavelength. We're 1 to 100 meters in wavelength, so big range here, and getting into very long wavelengths and like lengths we can think about. So radio waves are what is used in transmitting radio signals through the air to your car or wherever else you have a radio. And this is the lowest energy, lowest frequency, and longest wavelength end of the spectrum. So these are sort of the major classifications. Some of these will sometimes get broken down further into subsections, but a lot of these are things you've probably heard of at some point. And this is kind of the energy ranking. So basically anything UV and above in energy has the potential to be dangerous. Anything visible and below is too low energy to interact with matter in such a way that it causes any kind of chemical reaction. It can cause other things to happen within the molecules, but it's not going to actually cause the molecules to change. And that's the only way that any kind of damage can occur.